Hi folks. So in class we talked about the idea of an aggregation paradox, and we're about to see a really good example of one of those in the context of a regression model, specifically a model where we're going to have both a continuous and a grouping variable that enter into the prediction of some outcome. We'll do this in the context of the house.csv dataset, which I uploaded as part of the week 3 set of materials. Find that on the class website. So I've already surfed and clicked the import dataset and gone to the part of my hard drive where this house.csv file sits. Double check that everything's in order here. Yes, I've got a header row. Yes, the separator is a comma. Everything looks good. So I'll click import, and now I've got the house data set up here. Notice there's a lot of information here. The variable we're trying to forecast or predict is asking price of a house in dollars. Got a whole lot of information about each house, but the two we're going to focus on today are the size of the house as measured in square footage and the neighborhood that the house sits in. Here there are 3, and you can see you've got different ones for each row here. This one happens to be in neighborhood 2, this is in neighborhood 1, and so forth. Let's go back to the house.r script, which you can also find uploaded associated with the week 3 exercises. First thing to do here is to load the Mosaic library. That'll give me a few commands that aren't part of the baseline R package. And I've already imported the data set, so I'll plot the data. In this case, most obvious relationship you might imagine, bigger houses sell for more. We plot price versus square foot, and sure enough, we see that as square footage increases, so does the asking price of the house, with a pretty clear linear trend here. Now, if we wanted to fit a linear model, we are pretty used to doing that by now. I can fit the model and add the line to the plot there. But of course, that's not the only variable of interest here. Remember, one of the things we talked about in class is what happens when we estimate linear relationships between two variables, an x, square foot, and a y, price, where there are other potential grouping variables that might confound the relationship. So clearly we're getting a sensible relationship here between square foot and price, but is it the right relationship? We don't know. We should worry about aggregation paradoxes here. You'll notice in particular that we have many different houses here in neighborhood 1, and just about as many in neighborhood 2, just about as many in neighborhood 3. It might occur to you that because there are systematic differences in prices among different neighborhoods, at least in most of the areas that I'm familiar with, that the neighborhood grouping variable here could be confounding the price square foot relationship. Maybe not the direction here, this is a pretty sensible direction, but maybe confounding our estimate of the magnitude of that relationship. And sure enough, if we look at the mean price by neighborhood, this command right here will only work if you've loaded the Mosaic library, by the way. We notice that neighborhood 1 tends to be the cheapest, neighborhood 2 the middle one, neighborhood 3 the most expensive. Let's see what happens if we fit 3 different models for those 3 different neighborhoods. A really simple way to do this in R is to use the subset command. So the subset function takes 2 arguments. First, the data set that you want to subset, and second, the filter, which is a logical command that you apply to the function here. So in this case, we want those whose neighborhood variable, remember house is the data set, neighborhood is a variable that lives with inside the house data set. We want those whose values of the neighborhood variable are equal to this string right here. And whenever I'm dealing with strings, I have to enclose them in quotation marks in R. They could be single quotes, they could be double quotes. It doesn't matter as long as you're consistent. And then also notice the double equal sign right here for logical checking. The single equal sign is for variable assignment. The double equals is for checking. Okay, so with all those preliminaries out of the way, let me create these 3 subsets here, house.n1, n2, and n3 for the neighborhoods 1, 2, and 3, respectively. I'll just highlight that whole block of code right there, hit Command-Enter, and now I've got those 3 different data sets for the 44 houses in neighborhood 1, 45 in neighborhood 2, and 39 in neighborhood 3. I could also fit simply a separate model for neighborhood 1. Let's try that. So I'll plot price versus square foot for this subsetted data set that I've created right here. I'll use solid dots, PCH equals 19, and I'll make them blue. Now let me fit a linear model for this particular subset right here. You notice the syntax is exactly the same as for the lm_all object we created above, except instead of data equals house, I've got data equals house.n1, the data set I created right there. So I'll fit that line, save it in lm.n1, and I'll superimpose that line on the plot. So that's a fairly limited utility when I want to compare across neighborhoods. Really what I want here is to put all 3 sets of dots for all 3 different neighborhoods on the same plot, and then compare the lines that I get when I fit 3 individual models with the line that I get when I fit a single model that doesn't differentiate between neighborhoods. Okay, Okay, so let me go ahead and do that. Let me fit the two remaining linear models for neighborhood 2 here and neighborhood 3 here. And now let me plot all those points on the same plot here. So I'll go back and have open circles for the full data set, and now I'll add points using the points command, which obeys the same syntax as plot, or lm. And I'll use the n1, n2, and n3 subsets, putting those up in solid circles with blue, red, and gray points, respectively. So there we have it for neighborhood 1, neighborhood 2 in red, and neighborhood 3 in gray. And I can also superimpose the 3 separate lines. The line for neighborhood 1 in blue, neighborhood 2 in red, neighborhood 3 in gray. You notice these lines all look pretty similar in terms of having the same slope, but they are clearly shifted up. They all have different intercepts from one another, reflecting the fact that the points in neighborhood 3 tend to be the highest price on average, so highest intercept. Neighborhood 2 in red in the middle, the median intercept here, and neighborhood 1, the cheapest houses, that having the lowest intercept. I've actually given you a bit of syntax in here if you wanted to put a legend up. There it is. I won't explain it, but I'll let you use the $legend command to bring up the help page for the legend command if you wish. Let's go back to plots here, and if you wanted like a bigger version of this that you could print out, you can click on zoom. Okay, so we can clearly see neighborhood 1, neighborhood 2, neighborhood 3 right there. Bring that back to the small scale. Let me compare that very quickly with what happens when we put the line for the entire data set up there. And zoom back here. Notice what's different about these. These all three have roughly the same slope and different intercepts. This has, of course, one slope and one intercept for the full data set, and it's a different slope. And so this is evidence of a confounding relationship here, which, again, we talked about as an aggregation paradox, more generically a kind of confounding. The price-size relationship looks steeper if you ignore neighborhood here. See, that's a steeper line than it does if you fit 3 separate models for the different neighborhoods. Really good example of how confounding it can certainly change the direction of an estimate, but it can also change the magnitude of an estimate, which is just as important in many cases. Let's just verify that by looking at the coefficients. So I'll look at the coefficients for the neighborhood 1 model, the neighborhood 2 model, the neighborhood 3 model, and the model that doesn't take into account neighborhood and fits the entire data set with a single slope and a single intercept. And you notice that these 3 intercepts obviously are different. These 3 slopes are, well, they're a bit different. This is lower than these two. These two are almost identical. But they collectively, these 3, 40, 49, 49, are very different from the estimate of 70. And this would be very important, for example, if you were a tax assessor and you were interested, hey, somebody added a 1,000 square foot addition to their house. How much does that increase the value of their house? Well, you'd be in trouble if you said it was actually $70 per square foot, when in reality, regardless of which neighborhood you look in, it tends to be more like $40 to $50 a square foot. So there's an aggregation paradox in action, good example of confounding. But all of the syntax that we swept through, the business of splitting the data set out into 3 different subsets, fitting 3 different linear models, superimposing 3 sets of points, it's all useful, but all a bit cumbersome. And so I'm going to show you a shortcut, a really nice piece of what computer scientists like to call syntactic sugar for handling this very easily. Okay, so let's do this the short way. LM for price predicted by square foot times neighborhood. That's the little asterisk, and think of that as a times or multiplication symbol for the whole data set here, house. Now that should be a bit murky at this point. There's no clear intuition to what that's doing there, but let's just plow ahead and see what happens at the end of the day. So I'll fit that model. R doesn't complain, so it's clearly something has happened. I'll plot the original data set with open circles back here on the right. And now I'll superimpose the fitted values from LM2, this linear model that has somewhat murky syntax, plotted by square foot for the house data set, and I'll put them in gray. All right, so I'm plotting the fitted values. You notice I get 3 different clear lines over here, and these are, in fact, exactly the same 3 lines as when I went up and did that. Different colors. It's a little bit easier when you're specific and split it out that way to get the nice colors. But what I've done here is exactly the same. Let's go take a look at the coefficients and see what's going on here. So I'll look at the coefficients for this linear model that I fit, LM2, and I get a whole boatload of coefficients. This is sort of more than we're used to looking at, but let's sort of break this down piece by piece. These are returned in what I'll call baseline and offset form. Okay, so here's the baseline intercept, here's the baseline slope, and here baseline arbitrarily is defined to be neighborhood 1. And then it gives you offsets here, minus 7224 for neighborhood 2, 23,752 for neighborhood 3, and then it gives you square foot colon neighborhood 2, square foot colon neighborhood 3. These are offsets for the slope. Let's figure out how to read these. So you'll notice if I take the baseline intercept, 32,906 and a bit, and the baseline slope, 40.30 and a bit, and I add to them the offsets associated with neighborhood 2. So minus 7224 up here for the intercept, and 9.13 for the neighborhood 2 slope. Let's see what numbers I get. I get 25,682 and 11, and then I get 49.43 for the slope when I add those together. Let's go compare those with the coefficients from lm.n2, which you'll recall was the linear model we fit when we split out neighborhood 2 as an explicit subset. Sure enough, it's exactly the same. 25,682, 11, 25,682, 11, 49.43, 49.43. Okay, so now you can see how this syntax here of square foot times neighborhood is a really nice shortcut for splitting the data set into 3 subsets corresponding to this grouping variable, neighborhood, and fitting a separate model for square footage within each of those subsets. And you could convince yourself that this same kind of decomposition here of a baseline and offset holds for neighborhood 3 in addition to neighborhood 2. And what the analogy I would invoke here is with using the LM command to fit groupwise means. So you remember when we fit simple groupwise models for things like the mammal sleep data set, the chymotrypsin data set, we could simply use the mean function after having loaded the Mosaic library and get groupwise means for neighborhood 1, 2, and 3. Or we could use the LM command, LM for price on a categorical variable neighborhood. And you remember if we extracted the coefficients from that model, we got those returned in baseline plus offset form. So here 110, 154, 110, 154, so that's the baseline intercept or the group mean for neighborhood 1. And then notice what we get if we take that number, I'll copy and paste that, and we add to it this offset here for neighborhood 2. We get 125, 231, up here 125, 231, exactly the group mean for neighborhood 2. So there's a very explicit analogy between using LM to compute groupwise means here and getting a result that's returned in baseline plus offset form, and the way that when you use this continuous variable times grouping variable up here in an LM, you get the results for the coefficients returned in baseline here plus offset form. You just have to be aware that now there's 2 baselines. There's a baseline intercept and a baseline slope. And then for each group in your data set, neighborhood 2, there's an offset to the intercept and an offset to the slope. Both ways of handling it are doing exactly the same thing. They're fitting 3 separate lines for 3 different data sets. They're just giving you the information in different forms. In class, we'll talk about what happens if we want to constrain all 3 neighborhoods to have the same slope, but rather allow different intercepts. There's a subtly different syntax here using times rather than plus rather than times in the neighborhood LM here, but that is for a different tutorial.